Okay, let's talk about derivatives of inverses. So we have the inverse function theorem. So pause and read this. And what it says is you got yourself a function that has an inverse. If the function's not invertible, this doesn't even apply. So the function has an inverse and the function is differentiable. And the derivative of the inverse is not identically equal to 0. Or another way of saying that is this statement is true for any x values where the derivative evaluated at the inverse is not 0. Then the derivative of the inverse is 1 over the original function's derivative evaluated at the inverse. So that is just confusing sounding. Like students always get confused by this. We'll do a quick example. Then I'm going to use this to develop some inverse trig function derivatives, and then we're never going to talk about this again. Like you might have a couple of homework questions about this theorem, but I'm never going to make you use this theorem here on a test. Some of my colleagues do. Some of my colleagues will throw in a test question about this. I'm going to be honest with you. I've been teaching this class for 20 years. I don't even think I have this theorem memorized. Like I just don't find it that interesting. So we're not going to do a lot with this. I'll do an example or two, and then we'll just have a bunch of formulas that are derived using. Okay, so just for clarity, let's consider this guy. So I've got G is x plus 2 over x. That's a 1 over x. It's a 1-to-1 function, has an inverse. Let's find that inverse. So we do y equals x plus 2 over x. Then remember, you swap your x's and y's. So this is all college algebra here. X will be y plus 2 over y. Now we want to solve for y. So I'd multiply the y over. Y times x will be y plus 2. Get all my y's together. Factor a y out. And then divide. I would get y equals 2 over x minus 1. So that's my inverse. G inverse would be 2 over x minus 1. Okay, now, what's the point of this theorem? This theorem says, oh, sorry, I wrote inverse wrong. This is G inverse. That's G negative 1. I accidentally wrote a prime there. This theorem says the inverse's derivative would be 1 over the original function's derivative evaluated at this inverse that we just calculated. So let's calculate all that. And we'll do it both ways. We'll just actually find the inverse of this guy, and we'll do it this way, and we'll see that we get the same thing. So here's my original function G, x plus 2 over x. I would rewrite this by splitting the numerator 1 plus 2 over x. So x over x plus 2 over x. Then his derivative is really easy. Derivative of 1 is 0. Derivative of 2 over x would be negative 2 x to the negative 2, or negative 2 over x squared. If you can't just immediately see how I got this, you want to practice your derivatives a little more. So this theorem says the inverse's derivative, it's an x there, ugly x, is 1 over the inverse of G evaluated at the inverse. So I took the inverse and I plugged it in to that x. So the derivative of the inverse is 1 over, so that's why it's 1 over here. The original function's derivative evaluated at the inverse. Okay, now we're going to do a whole bunch of cleanup there. So I've got a fraction divided by a fraction. That's keep, change, flip. So this would be 2 over x minus 1. Let me write that prettier. 2 over x minus 1 squared over -2. So I just flip this fraction over. This will now be at the top, that'll be the bottom. And then I can do another keep, change, flip, and these will cancel, and I get -1 over x minus 1 squared. Now, what if we just did from the derivative or from the inverse? My inverse, I claimed, was 2 over x minus 1. What if I just took this guy's derivative? Well, this guy is, I feel like I'm missing a 2 here. Hold on. Yeah, see it. Hold on, a 2. I got an extra 2 in here. Let me erase all this. Probably should have erased before I hit record again, huh? Okay, let me start back here. That what I had that written there was wrong. So G prime, G inverse prime is 1 over the original's derivative evaluated at the inverse. The original's derivative is -2 over the input squared. What is my input? The inverse, 2 over x minus 1. Okay, that was right, but then I forgot to square this 2. All right, so we're going to do some keep, change, flip. So this would be 2 over x minus 1 squared over -2, which would be 4 over x minus 1 squared times -1/2. And we get -2 over x minus 1 squared. That's using the inverse theorem. Or we already know the inverse of our function. Our inverse was right here, 2 over x minus 1. We could just take this guy's derivative directly by just using chain rule here. I would write that as 2 times x minus 1 to the -1 power. Then his derivative, bring the power down. -1 times 2 is -2. And then the power drops down by 1. We get a -2. We get exactly the same answer. This was so much simpler than going through all that. I would never, ever want to do that if I had another way. So we could do this one if we wanted to using the inverse function theorem, but it's going to be really nasty. Like, I'm not a big fan of this theorem. So I'm not going to do that. Now, we can use the inverse derivative theorem to prove this statement that I've already made a couple of times, that when you have x raised to any power, here we're just doing it for rational numbers, this works for any number. The derivative of x raised to any real number power, bring that real number down, and then that number drops down by 1. where A is any real number. And you can prove this using the inverse derivative theorem. I'm not going to. I want to prove one of these. It's the only thing I'm going to use it for. I'm going to prove this first one. And then what we're going to take from this section is you're going to write all these formulas down in your notes. And we're just going to take all of these as proven. I'll show you how we prove one. The rest of them we're just going to believe. Okay, so I claim that the derivative with respect to x of inverse sine of x is 1 over square root of 1 minus x squared. So that's not the reciprocal of sine, that's arc sine, that's inverse sine. Okay, and how will we get this? Well, if we've got f of x equals sine of x, then f inverse of x would be inverse sine. Then the inverse derivative theorem says the derivative of the inverse will be 1 over the original function f's derivative evaluated at the inverse. So I need to find the original function's derivative. And we all know, hopefully, the derivative of sine is cosine. So this says the derivative of arc sine. So I'll write that here. Inverse sine of x, his derivative will be 1 over the other guy's derivative, cosine, evaluated at inverse sine. Okay. Now, this problem here is something that you did back in trig. You don't remember it, but you did problems like this back in trig. So now we're doing a little side work here. I want to evaluate or find or simplify cosine of the inverse sine of x. So remember, sine and cosine tangent, you give them an angle, they spit out a fraction. The arguments, the inputs are angles, the outputs are fractions. Inverse trig functions do the opposite. You hand them a fraction, they spit out an angle. Inverse sine will spit out angles, and then I would take cosine of that angle. So this thing here, this is just some angle in a triangle. Let's give it a name. Let's call that theta. So if I were to draw some triangle here, theta is just an angle in a right triangle. So what am I really asking for here? I really want cosine of theta. That's theta. Theta is the inverse sine of x. So if I take the sine of both sides, sine of theta will be sine of the inverse sine of x. And as long as we were in the correct domain, these two functions will cancel each other out, leaving just x. So sine of theta equals x. I'm going to write that as x over 1. I know what sine is. Sine's opposite over hypotenuse. So from this angle theta, opposite hypotenuse. Sine is x over 1. How are we going to find this side? Pythagorean. A squared plus b squared equals c squared. So maybe we'll call this guy a. A squared plus x squared will equal 1 squared. Or a squared equals 1 minus x squared, or a equals square root of 1 minus x squared. Now, technically, we would need a plus or minus there, but because of the domain we're in, we know we want a positive value here. So this side is square root of 1 minus x squared. Now, remember what we were trying to find. We want cosine of theta. Make all this a little smaller. So we want cosine of theta. We can look at the picture and figure out cosine of theta. Cosine of theta will be adjacent over hypotenuse. Root 1 minus x squared over 1. Okay, so right there, that's what that was. 1 over, that was theta. Cosine of theta was square root of 1 minus x squared. So now we have just proven this formula right here. All these other ones are very similar in derivation to that. I'm not going to go through all of them. This one we're going to use a lot. This is one of the most popular inverse function derivatives. This one you just want to memorize. The derivative of arctangent of x is 1 over 1 plus x squared. The rest of these, I've never bothered to memorize. If we need them, like I'll give you a formula. Like test 2 that's coming up, at the top of the test is a formula sheet, and it's literally just these 6. You don't have to memorize these, but this one you're going to use so much, you're probably going to remember it. All right, let's do an example. Okay, so let's say we want to have tangent of something, arctangent of something. Well, we're going to have to use chain rule. So the derivative of arctangent of anything is 1 over 1 plus that thing squared times the derivative of what's inside. This is chain rule. I've got a function inside a function. So times 2x. So that would be 2x over 1 plus x to the 4th. What about the derivative of arcsecant, inverse secant of 1 over x? I don't remember that guy's derivative. I'm going to look it up. It's right here. The derivative of inverse secant of junk is 1 over absolute value of junk times junk squared minus 1 times the derivative of junk. If this is a function, we're going to chain rule this and have the derivative of whatever's inside. So the derivative of inverse secant of 1 over x will be 1 over absolute value of junk times square root of junk squared minus 1. I'm checking to make sure I got that. Yep. Times the derivative of what's inside. That's a function inside a function. The derivative of 1 over x is negative 1 over x squared. Okay, so that's how we'll be using these. These formulas will be given to us, and we're going to plug and chug. Where do they come from? The derivative of an inverse function theorem. It's a good place to stop there.